Billions of years ago, in a flash of existence so brief it almost, well, it defies human comprehension. The universe as we know it just sprung forth. It's a concept that it never fails to send a shiver down my spine, doesn't it?
It really is mind-boggling.
But here's where the cosmic plot truly thickens. The story didn't just stop there. In fact, our universe is still expanding, and not just expanding, but accelerating, speeding up faster than we ever imagined.
That acceleration is the real kicker.
This ongoing runaway growth is truly one of the most profound cosmic puzzles we face today. So what's driving this incredible, accelerating cosmic expansion? What unseen forces are at play here?
That's the billion-dollar question, isn't it?
Yeah.
Or maybe trillion-dollar, given the scale.
Right. So today we're embarking on a deep dive into that very mystery behind our universe's dramatic growth spurt. We're going to unpack the stunning, yet still debated legacy of cosmic inflation. We'll explore the elusive and, well, dominant force we call dark energy.
The big one.
And then confront one of cosmology's most pressing dilemmas, the perplexing Hubble tension, a cosmic headache that's challenging our foundational understanding of reality itself.
It really is shaking things up.
Think of this as a grand detective story. We're sifting through the evidence, examining the theories, and piecing together tantalizing clues about the universe's past, its accelerating present, and its enigmatic future expansion. Welcome to the great escape of space-time.
Let's do it.
Let's begin this cosmic journey by going right back to the beginning. For decades, ever since the groundbreaking detection of the cosmic microwave background, or CMB, back in 1965.
A pivotal moment.
Absolutely. The Big Bang model has stood as our most accepted and successful explanation for the universe's evolution. It describes how everything we observe today, from the smallest subatomic particles to the grandest galaxy clusters, originated from an incredibly hot, dense state and has been evolving ever since.
It's the cornerstone, really. The foundation we build upon.
It truly is the bedrock of modern cosmology. But, as with all robust scientific theories, the Big Bang model, even with its immense successes, left some truly perplexing questions unanswered. It was these nagging inconsistencies that paved the way for a revolutionary idea: cosmic inflation.
Right. The standard Big Bang needed a little help explaining some things.
This concept, inflation, steps in to fill those crucial gaps, refining our understanding of the universe's earliest moments. At its core, cosmic inflation describes a period of unbelievably rapid, quasi-exponential expansion that occurred mere fractions of a second after the Big Bang.
And when you say rapid,
I mean, incredibly rapid, faster than you can even formulate the phrase cosmic explosion. It was so swift, in fact, that it describes an expansion of space-time itself, effectively faster than light.
which sounds like it breaks the rules, but it doesn't.
Exactly. This isn't a violation of Einstein's speed limit, because that limit only applies to objects within the universe moving through space, not the fabric of space itself expanding.
A key distinction. The universe itself can stretch faster than light can cross it.
To visualize this incredibly complex idea simply, imagine blowing up a balloon. At first, it's just a small, wrinkled glob. But with a few good puffs, it gets huge and remarkably smooth very, very quickly. That's inflation's core effect in a nutshell.
That's a great analogy. And what's truly remarkable here is how elegantly and effectively inflation resolves several fundamental puzzles that the Big Bang model, on its own, really struggled to explain.
Like what? What were the big ones?
Well, let's start with the flatness problem. Einstein's general theory of relativity, which governs gravity, famously tells us that mass and energy should curve space and time. So intuitively, you might expect a universe like ours, which is brimming with matter and energy, to have some overall curvature.
Right, like a sphere or maybe a saddle shape.
Exactly. Either positively curved, like the surface of a ball, or negatively curved, like a saddle. But the perplexing observation, our universe, on large scales, appears darn nearly flat.
And not just sort of flat, but really flat.
Incredibly flat. Observations, especially from the CMB, pin it down to within about 0.4%. Without inflation, this observed flatness would require an almost impossibly fine-tuned initial condition at the Big Bang.
Like winning the cosmic lottery levels of fine-tuning.
Precisely. Literally, the universe would have had to begin with an energy density deviating by no more than 1 part in 10 to the power of 60 from the critical density for it to appear flat today. It's just absurdly fine-tuned.
Wow.
Inflation elegantly solves this cosmic fine-tuning. The incredibly rapid expansion ironed out wrinkles in the early chaotic universe, making it appear flat on cosmic scales.
Just like that balloon analogy, a small patch on a huge balloon looks flat.
Exactly. It smooths out any initial curvature automatically. No fine-tuning needed.
Okay, that's clever. What else did it fix?
Then there's the equally perplexing horizon problem. This refers to the observation that distant parts of the universe, which are now so far apart that light hasn't had time to travel between them since the Big Bang, still appear to have roughly the same temperature.
Right, I remember this one. How can places that have never been in touch, so to speak, have the same temperature? Seems impossible.
It seems to assault the fundamental laws of thermodynamics, which state that for regions to reach thermal equilibrium to even things out, they need to be in causal contact. Heat needs time to flow. So how could these causally disconnected regions be in such uniform thermal equilibrium?
Yeah.
Inflation provides a powerful answer. It posits that these far-flung parts of the universe, which are now causally disconnected and appear beyond each other's horizons, were once in very close, intimate contact before or during the inflationary period.
Ah, so they were connected way back then.
Exactly. During this fleeting moment, they had plenty of time to swap heat and equalize their temperatures before they were stretched apart by this hyper-rapid expansion well beyond each other's causal horizons.
So the uniform temperature we see in the CMB today is like an echo from that early connected time.
Precisely. It's a direct relic of that brief connected past, a uniform echo of a once unified cosmic soup. Inflation basically took a tiny uniform patch and blew it up to encompass our entire observable universe.
Okay, so it solves flatness and this horizon issue. It sounds like a pretty solid addition to the model.
It's incredibly successful at solving these problems, yes. And it's now a built-in, though still actively researched, piece of our standard story of cosmic evolution, the Lambda CDM model we'll get to.
But you said actively researched and debated, so it's not completely settled.
Well, it's not without its controversies and remaining questions. For example, back in 2014, there was a huge buzz, a significant claim of detecting ripples from inflation, known as primordial gravitational waves, imprinted on the cosmic microwave background.
Oh, yeah, I remember that BICFP2, wasn't it? Huge news.
That's the one. It generated tremendous excitement across the scientific community. But unfortunately, upon further analysis, this detection proved mistaken.
Ah, right. It turned out to be dust in our own galaxy mimicking the signal.
Exactly. Foreground dust contamination. It was a huge blow to researchers who had spent years searching for such evidence. It highlights how science, especially at the frontiers, is a continuous process of rigorous testing and refinement. Even exciting initial results must withstand intense scrutiny.
A tough lesson, but that's how science works, I guess. What other questions remain?
Beyond finding direct evidence like those gravitational waves, there's still the fundamental question. What physical mechanism actually made the early universe inflate in the first place? What is the inflation field, assuming it exists?
We don't actually know what drove it.
We have models, hypothetical scalar fields, but no definitive answer. And once it starts, inflation, driven by this hypothetical inflaton field, is incredibly difficult to stop globally, which leads to some truly speculative and mind-bending ideas.
Like the multiverse.
Like the multiverse theory, yes. This suggests that our universe is just one of many, with causally disconnected universes eternally budding off from one another due to runaway or eternal inflation in different regions. It's a concept that arises directly from the mathematics of many inflation models.
Wow. So our universe could be just one bubble in a cosmic foam.
That's one way to picture it, yeah. Highly speculative, of course, but a logical consequence of some models.
Are there any other ideas out there, maybe alternatives to inflation itself?
Some alternative ideas have been proposed to address aspects like the horizon problem, though they often struggle with the flatness problem or generating the right kind of density fluctuations we see. One such idea is a variable speed of light.
The speed of light wasn't always constant. That sounds radical.
It is radical. If the speed of light was significantly faster in the very early universe, that could also explain the horizon problem, as light would have had more time to travel between regions. Some theorists even speculate that light might still be slowing down now, just imperceptibly.
But wouldn't that mess with all of physics?
It would require a fundamental rewriting of physics, yes. Challenging the constancy of fundamental constants is a very big step, and there's currently no compelling evidence for it. Inflation remains the leading paradigm because it solves multiple problems within the existing framework of physics.
Okay, so inflation, despite some open questions, gives us this incredibly powerful elegant explanation for the universe's initial uniformity and its observed flatness. It takes us from a tiny quantum speck to a vast, smooth canvas in an instant.
Pretty much, yeah. Setting the stage.
But the story of cosmic expansion didn't end there once inflation subsided. In fact, after a period where gravity was slowing things down as expected, it took another surprising turn.
A very surprising turn.
Let's fast forward billions of years. Past the era when gravity was expected to gradually slow down the universe's expansion due to the immense gravitational pull of all the matter within it. That makes intuitive sense, right? Gravity pulls things together.
Absolutely. That was the standard expectation for decades. The only question seemed to be whether there was enough gravity to eventually stop the expansion and cause a big crunch, or if it would just coast forever, slowing down but never quite stopping.
But then, in 1998, something truly unexpected and revolutionary happened. Two independent research projects, the Supernova Cosmology Project and the High-Z Supernova Search Team, made a groundbreaking discovery.
Using those Type Ia supernova we mentioned earlier.
Right, and they found that the universe's expansion wasn't slowing down at all. It was actually speeding up.
A monumental, truly startling surprise. It flew in the face of everything we thought we knew.
It must have sent shockwaves through the scientific community. It defied all prevailing expectations and calculations at the time, and deservedly, 3 members of these pioneering groups subsequently were awarded Nobel Prizes for this revolutionary finding in 2011.
Saul Perlmutter, Brian Schmidt, and Adam Rees. A well-deserved prize for turning cosmology on its head.
Absolutely. So tell us about the evidence. How did these supernovae reveal this acceleration?
Okay, the primary evidence came from meticulously observing these Type Ia supernovae. As we touched on, these aren't just any exploding stars. They're incredibly precise cosmic tools, often referred to as standard candles.
Standard candles because they shine with a known brightness.
Almost exactly, yes. The theory is they mostly originate from white dwarf stars in binary systems. The white dwarf pulls matter off its companion star until it reaches a critical mass limit, the Chandrasekhar limit, about 1.4 times the mass of our sun.
And then boom.
And then boom, a runaway thermonuclear explosion. Because they all explode at roughly the same mass, they all reach almost exactly the same peak intrinsic brightness when they detonate. They're incredibly luminous, too, briefly outshining entire galaxies, so we can see them across vast distances.
Okay, so we know how bright they should be intrinsically.
Exactly. So because we know their intrinsic brightness with remarkable accuracy, we can use their observed brightness to measure their distance from us. It's simple inverse square law. If a standard candle appears dimmer, it must be farther away.
Makes sense.
The process involves repeatedly imaging selected areas of the sky to discover these supernovae. They're following up with observations to record their peak brightness over weeks. Crucially, they also measure the redshift of the supernova's light, or its host galaxy.
And redshift tells us how much the universe has expanded since the light left the supernova.
Right. It tells us how fast it was moving away from us due to cosmic expansion at that time. So you have distance from brightness and velocity or expansion history from redshift.
So what were they expecting to see?
Cosmologists had largely expected that the further away these supernovae were, meaning higher redshift, looking further back in time, the more their light would have been stretched and dimmed by a universe that was decelerating due to gravity. Think of it like a ball thrown upwards that slows down.
So distant supernovae should have appeared brighter than a certain amount because the universe wasn't expanding as fast back then.
Effectively, yes, compared to a universe expanding at a constant rate or accelerating. If the universe was decelerating, the expansion was faster in the past, meaning the supernovae wouldn't be quite as far away for a given redshift as you might think. But the unexpected result from both research teams was
They were dimmer.
They were dimmer. The distances of the high redshift SNE were, on average, 10% to 15% further than expected, in a universe that lacked a cosmological constant or wasn't accelerating. This means they appeared fainter than they should have been.
Which implies they were further away than predicted if gravity was just slowing things down.
Exactly. For an accelerating universe, the scale factor's second derivative, think of it as the cosmic accelerator pedal, is positive. This means the expansion rate was actually smaller in the past than it is now.
Okay, slower in the past means.
It means light from those distant supernovae had to travel for a longer time to reach us, through space that expanded more than expected during its journey. A longer light travel time implies a larger actual distance and consequently fainter supernovae.
And that matched what they saw.
Perfectly matched the actual observations. It was direct observational proof of a universe not just expanding, but actively putting its foot on the gas pedal.
Wow. So if gravity should be slowing things down, what in the cosmos is putting its foot on the accelerator? What mysterious entity is defying our understanding of how the universe should behave?
That's where we introduce the leading, albeit still enigmatic, explanation. Dark energy.
Dark energy. The name itself sounds mysterious.
It is. It's a placeholder name, really, for whatever is causing this observed acceleration. But based on our models, cosmologists estimate it makes up a staggering 68% of the entire universe's total energy density.
68%. That's most of the universe.
The vast majority. Ordinary matter, the stuff that makes up stars, planets, us,
Yeah.
that's only about 5%. The 27% is dark matter, which we also can't see directly, but interacts gravitationally. So yeah, we only understand about 5% of the cosmic pie.
That's truly astonishing. So what does this all mean for the fundamental nature of reality? What is this stuff?
Well, that's the big question. But what's truly compelling here is understanding the properties dark energy must have within the framework of general relativity to cause this acceleration. Its most crucial property is that it possesses negative pressure.
Negative pressure, like anti-gravity.
In effect, yes. It exerts a repulsive rather than an attractive gravitational action. Think of regular pressure, like in a balloon, pushing outwards. Negative pressure in a gravitational context also pushes outwards, effectively stretching space apart.
Okay.
And unlike ordinary matter or radiation, whose energy density dilutes as the universe expands, same stuff spread over more volume.
Right. It gets thinner.
Dark energy, particularly in its simplest form, seems to have a constant energy density. It doesn't thin out as space expands.
Wait, how can that be? More space, same density. Where does the energy come from?
That's one of the deepest mysteries. It seems to be a property of space itself. As more space is created through expansion, more dark energy appears to maintain the constant density. This is key to how it drives cosmic acceleration. Because its density doesn't drop, its repulsive effect grows proportionally stronger as space expands, eventually overcoming the attractive pull of matter and radiation.
So the more the universe expands, the stronger the push from dark energy becomes.
Relatively speaking, yes. Its total effect increases as the volume increases, while matter's gravitational pull weakens as it spreads out.
Okay. Is there an equation for this?
There is. The relationship between pressure and energy density for dark energy is described by an equation of state, often written as P/W is C2. Here, C is the speed of light, and W is the crucial parameter. For cosmic acceleration, remember, positive second derivative of the scale factor, the universe's pedometer needle moving up W needs to be less than -13.
Less than -1/3. Okay.
Ordinary matter has W equals 0. Radiation has W as +13. So dark energy is fundamentally different. Now, the simplest and most widely accepted explanation for dark energy is that it's a cosmological constant, often denoted by the Greek letter lambda.
Einstein's cosmological constant, didn't he call that his biggest blunder?
He did initially. He introduced it to keep the universe static before Hubble discovered expansion. When expansion was found, Einstein discarded it. But maybe he was right for the wrong reasons. A cosmological constant corresponds to the energy of empty space itself, vacuum energy. And for a cosmological constant, W is precisely -1.
W equals -1. So its energy density stays perfectly constant as the universe expands.
Exactly. This specific form of dark energy, lambda, when combined with cold dark matter, CDM, gives us the lambda CDM model, and ACDM. This model has been the standard model of cosmology since around 2003.
Why? Because it fits the data best.
Primarily, yes. It aligns remarkably well with a wide variety of cosmic observations, those pivotal supernova findings, the detailed structure of the cosmic microwave background, the large-scale distribution of galaxies, baryonic acoustic oscillations. It just works surprisingly well. The supernova observations, in particular, strongly favored expanding models with a positive cosmological constant and, crucially, an accelerating expansion with W close to magnitude 1.
So case closed. It's lambda.
Not necessarily. While the cosmological constant is the simplest explanation and fits the data well so far, it comes with its own huge theoretical problems, like why its value is so incredibly small compared to theoretical predictions from particle physics, the cosmological constant problem. So alternative ideas for dark energy have been rigorously explored.
Like what? What else could it be?
One such idea is quintessence. This is a proposed form of dark energy with a non-constant state equation. So W wouldn't be exactly maybe 1, and its energy density could decrease slowly with time, unlike the cosmological constant.
So it's more dynamic.
Exactly. Quintessence is considered a more dynamic form of dark energy, often modeled as a slowly evolving scalar field, similar in concept to the Inslaton field, but operating today. Its energy density and W value could change over the universe's history.
Could we tell the difference between quintessence and lambda?
Potentially, yes, with precise enough measurements of the expansion history over time. If W is found to be different from -1,1 or changing, that would rule out lambda and point towards something like quintessence. Current data is consistent with W Germanic 1,1, but there's still some wiggle room.
Okay. Any other contenders?
There's a more dramatic and, frankly, unsettling alternative called phantom energy.
Phantom energy. Sounds spooky.
It is a bit. This exotic form of dark energy would have a W value less than -1.
Wait, less than -1? I thought -1 was the limit for the cosmological constant.
It is for many standard theories, but theoretically, WH1 is possible, though it violates certain energy conditions often assumed in physics. Phantom energy is a truly wild scenario. Here, the dark energy doesn't just stay constant or slowly decrease. Its density increases as the universe expands.
It gets stronger over time. How is that possible?
Again, it's theoretically challenging, but the implication is profound. If phantom energy exists, its density would become infinite in a finite amount of time. This would generate such huge gravitational repulsion that the universe would lose all structure and end in a big rip.
A big rip. What does that mean?
It means the expansion becomes so violent it overcomes all other forces. First, galaxy clusters would be torn apart, then galaxies themselves, then solar systems, stars, planets. Eventually, even atoms and atomic nuclei would be ripped asunder. Everything dissolves into fundamental particles flying apart infinitely fast.
That's terrifying. How soon could that happen?
It depends on the exact value of W. To give you a chilling sense of the timescale, for a W value of, say, -32 and a current Hubble constant of 70 kilometers MPC, the Big Rip is estimated to be about 22 billion years away.
Okay, so not tomorrow, but still a definite end.
A very dramatic and definitive end. Current observations slightly favor W negative 1, but the uncertainty is still large enough to include W equals 1 as lambda and even W1 nec as quintessence. So the Big Rip remains a possibility, but not a certainty.
It's truly mind-bending to consider the implications. This dark energy isn't just expanding the universe. In some scenarios, it's literally tearing it apart at an accelerating rate. It forces us to rethink our entire understanding of the universe's ultimate fate.
Absolutely. It shifts our perspective dramatically.
And this accelerating expansion, alongside that incredibly rapid early inflationary period, it naturally raises another fascinating question. Are these two cosmic speedups connected? Could they perhaps be two different acts in the same cosmic play, driven by the same actor?
That's a very deep and appealing question for physicists. Could there be a unified explanation?
This brings us to a grand question that cosmologists are actively exploring and debating. What if both the rapid early expansion, that initial burst of inflation, and the slower yet still accelerating late-time expansion we observe today could be explained by a single underlying phenomenon?
A unified theory of cosmic acceleration.
Exactly. It's a powerful idea of cosmic unification, seeking to simplify the universe's most dramatic epochs. This is precisely the realm of quintessential inflation.
Right. This idea suggests that one kind of energy can explain both the early, incredibly rapid inflationary expansion and the current accelerating expansion driven by what we call dark energy.
It's like having a cosmic Swiss Army knife, a single fundamental field or force that governs both the birth and the ultimate destiny of the universe.
That's the goal. Quintessential inflation proposes a unified model, suggesting a single evolving scalar field is responsible for both eras. It's an attempt to streamline our cosmological understanding, to find a common root for these two distinct yet equally dramatic periods of rapid growth.
So how would that work? How could one field do both jobs?
The challenge is in designing a single field, whose behavior changes dramatically over cosmic time. It needs to start with the right properties to drive that incredibly rapid inflation very early on. Then, its energy needs to somehow convert into the matter and radiation we see today. And finally, much, much later, its residual energy needs to kick back in or evolve to act like dark energy and drive the current acceleration.
That sounds complicated. Getting one field to wear so many hats.
It is complicated, but potentially very elegant if it works. A critical process within this unified framework, and indeed essential to any standard cosmological model involving inflation, is what's known as reheating.
Reheating, okay, what's that?
Here's why it's so necessary. After the universe expands so incredibly rapidly during inflation, it cools down dramatically. The energy density of any normal matter or radiation plummets. Inflation leaves behind an incredibly sparse and cold void, largely empty of the particles we see today.
Like you said, a cold pizza left out too long.
Exactly. But for anything to form later, for quarks and electrons to combine into protons and neutrons, for nucleosynthesis to happen, for stars to ignite, galaxies to form, and eventually for life to arise, the universe needs to heat back up again. It needs to be filled with a hot soup of particles.
So reheating is like jump-starting the hot Big Bang.
That's a perfect way to put it. This reheating process is like giving the universe a warm-up to get it back into shape. It's where the energy stored in the inflaton field, or the quintessential inflation field, gets converted into the particles that make up the hot, dense Big Bang plasma. It's a crucial cosmic snack break, if you will, filling the universe with the ingredients for its subsequent evolution.
How does that energy conversion happen?
Scientists have proposed a couple of primary mechanisms. The first is instant preheating. This is, as the name suggests, very fast and efficient, like a microwave for the universe.
Zap, instant particles.
Pretty much. It happens really fast, and boom, the universe heats up quickly. This mechanism requires very specific conditions dictated by quantum field theory, where the inflaton field oscillates rapidly after inflation ends, and these oscillations resonantly amplify quantum fluctuations, quickly transferring energy into a cascade of elementary particles. It transforms that cold void into a hot, dense, particle-filled space.
Okay, that's one way. What's the other?
The other main idea is gravitational reheating. This works a bit differently. It's as if gravity itself is the chef, stirring up ingredients to create particles.
Gravity makes particles.
This method doesn't rely so much on specific particle physics interactions between the inflaton and other fields. Instead, it hinges on the dynamics of space-time itself and the strong, rapidly changing gravitational effects during the very end of inflation. It's described as being like throwing a party where everything happens naturally without much planning. The idea is that gravitational interactions during this turbulent transition phase can spontaneously generate particles directly from the vacuum energy associated with the gravitational field itself.
So particles just pop out of space-time because it's shaking so much.
That's the gist of it, yeah. Reheating the cosmos through purely gravitational means.
Can we tell which mechanism, if either, actually happened?
That's a tough observational challenge. The details of reheating can leave subtle imprints on the universe's early evolution, potentially affecting things like the precise spectrum of fluctuations in the CMB or the abundance of certain relics, like gravitational waves produced during inflation. By accurately determining reheating temperatures, which might be possible through future, more sensitive observation scientists might predict how they relate to the rates of cosmic expansion during and after inflation.
So there's a link between how the universe reheated and how it expanded.
Potentially, yes. The efficiency and temperature of reheating can influence the subsequent evolution. This connection offers a tantalizing path toward testing these ideas and perhaps validating or ruling out specific inflation or quintessential inflation models.
So it's not just about what caused these two distinct periods of rapid expansion, but also how the universe transitioned from one phase to the next, reheating and setting the stage for everything we see today. It paints a more complete, continuous picture.
Exactly, connecting the dots from the very beginning to now.
But all these theoretical connections and our increasingly precise measurements inevitably lead us to one of the biggest, most urgent puzzles in modern cosmology. Something that has become a true crisis, a cosmic headache for physicists.
Yeah, this is where things get really sticky right now.
This is, of course, the infamous Hubble tension. To visualize this, simply, imagine two friends trying to agree on how fast they should be walking. One, relying on a deeply rooted, consistent understanding of their shared history, like looking back at how far they've come since the beginning, insists they're walking at a slow, leisurely pace.
Okay.
The other, using a direct, immediate measurement with a stopwatch right now, says it's more like a quick, brisk stroll, and they just cannot reconcile their measurements. Their watches don't agree.
That's a pretty good analogy for what we see with measurements of the Hubble constant H.
Right. H tells us how quickly the universe is expanding right now. And there's this persistent, troubling discrepancy between different ways of measuring it, and it's not going away.
It's become arguably the biggest problem in cosmology today.
So why is this Hubble constant so important anyway? Why does this discrepancy matter so much?
The significance of the Hubble constant cannot be overstated. It provides essential information about the size, age, and fate of the universe. Think of it like charting how much a tiny seed, representing the universe's early moments, has sprouted over billions of years into its present vastly expanded form. HR is the current growth rate of that sprout.
It sets the scale for everything.
Exactly. It scales distances, ages, and influences the balance between gravity and expansion, determining the universe's ultimate fate. The problem is, this cosmic growth curve doesn't seem to add up perfectly if our standard cosmological models are entirely correct. As Dan Skolnick, a lead researcher in this field, aptly puts it, we know what the universe looked like as a baby at the time of the Big Bang, and we know what it looks like today. But how it got from that tiny hot origin to its current vastness, if our standard models are correct, is still an open question. Current observational measurements don't connect those dots seamlessly.
That lack of connection sounds like a big red flag.
It signifies a fundamental crack in our understanding, potentially.
So how do we measure H-years? What are these two conflicting methods?
Okay, historically, scientists have measured the Hubble constant using two primary, very different methods. The first method involves early universe measurements, primarily by studying the cosmic microwave background, the CMB.
The afterglow of the Big Bang again?
Right. This is the faint remnant radiation from the Big Bang, the oldest light in the universe, essentially a snapshot of the universe when it was only about 380,000 years old. Using exquisite data from missions like the European Space Agency's Planck satellite, cosmologists analyzed the subtle temperature fluctuations, the tiny hot and cold spots in the CMB.
Those famous maps of the early universe.
Exactly. Those fluctuations act as a fossil record of the early universe's composition, how much dark matter, ordinary matter, neutrinos, etc., and its expansion rate back then. From these fluctuations, particularly the characteristic size of those spots, they can infer the initial conditions and, crucially, predict what the current expansion rate should be today if the lambda CDM model is accurate.
So it's an indirect measurement based on the standard model.
It's an inferred value, yes, based on fitting the lambda CDM model to the incredibly precise CMB data. These measurements suggest that the universe's expansion rate today, HU, should be around 67.4 kilometers per second per megaparsec.
Okay, 67.4, let's remember that number. What's a megaparsec again?
A megaparsec is a unit of distance used in astronomy. It's roughly 3.26 million light years. So 67.4 kilometers MPC means that for every 3.26 million light years further away a galaxy is, it appears to be receding from us about 67.4 kilometers per second faster due to cosmic expansion.
Got it. So that's the prediction from the early universe, assuming lambda CDM. What's the other method?
The second method uses local universe measurements. This involves direct observations of objects much closer to us in cosmic time, typically within the last few billion years. Astronomers measure galaxies' movement directly using precise cosmic distance markers.
Like those Type Ia supernovae again?
Exactly. Using standard candles like Type Ia supernovae and also Cepheid variable stars, pulsating stars whose period tells us their intrinsic brightness. There are also standard rulers, like baryon acoustic oscillations, which we can discuss more later. These methods build up a cosmic distance ladder to measure distances directly.
Measuring distances and redshifts nearby, essentially.
Right. These methods, meticulously calibrated and cross-checked, estimate the expansion rate to be significantly faster. The most prominent results, like those from the S80ES, supernova 80 for the equation of state of dark energy team, using Cepheids and supernovae, find values ranging from around 73 to 76 kilometers per megaparsec.
Wait, 73 to 76 compared to 67.4, that's quite different.
It's significantly different, much higher than the CMB predictions, a stark and persistent difference of about 9%.
9% might not sound huge, but in precision cosmology,
It's enormous. The error bars on both measurements have shrunk considerably over the years, and the discrepancy remains, even growing in statistical significance. It's now often quoted at over 5 standard deviations, or 5 sigma.
5 sigma. Isn't that the gold standard for discovery in particle physics?
It is. It means the probability of this difference being just a random statistical fluke is incredibly tiny, less than 1 in 3.5 million.
Wow. So this discrepancy, the Hubble tension, has been puzzling the scientific community for nearly a decade. What did people think was causing it initially?
For years, there were heated debates. Was it subtle measurement errors in one or both methods? Unknown systematic effects. Maybe the calibration of the standard candles wasn't quite right, or maybe there was some subtle feature in the CMB analysis we missed.
People hoped it was just an error that would go away with better data.
Many did, yes. That would be the simplest solution. However, as the precision of both types of measurements has improved dramatically, the discrepancy has only become sharper, more statistically significant. It just hasn't gone away. As Skolnick noted, we're at a point where we're pressing really hard against the models we've been using for 2.5 decades, and we're seeing that things aren't matching up.
That really signifies a growing consensus that the tension is real. It's likely telling us something new and unexpected about the universe.
That's increasingly the view. It might be more than just an error. It might be physics.
And speaking of pressing hard against models and refining measurements, this is where the latest research from Dan Skolnick's team at Duke University comes in, aiming to shore up these local measurements even further.
Right, trying to nail down that local value with maximum confidence.
Their strategy relies on enhancing something astronomers call the cosmic distance ladder. Can you explain that a bit more?
Sure, think of it literally like climbing a ladder to measure cosmic distances. Each rung represents a different distance measurement technique, suitable for different distance scales.
Okay.
The first lowest rung is the most direct and precise things like parallax measurements using the Earth's orbit to gauge distances to nearby stars in our own galaxy. Super accurate, but only works for relatively close objects.
Like measuring the width of a river using triangulation from 2 points on the bank.
Exactly. Then you use those nearby stars, whose distances you know accurately, to calibrate the next rung, maybe Cepheid variable stars found in those same nearby galaxies. You figure out the exact relationship between their pulsation period and their intrinsic brightness using the ones with known parallax distances.
Okay, so parallax calibrates Cepheids.
Right. Now you can use Cepheids, which are much brighter than typical stars, to measure distances to slightly further galaxies, where you can still resolve individual Cepheids. Then you find galaxies that host both Cepheids and Type Ia supernovae.
Ah, the standard candles again.
Use Cepheid distances to calibrate the true peak brightness of Type Ia supernovae in those galaxies. Once you've done that, you can use Type Ia supernovae, which are incredibly bright and visible across billions of light years, as your final rung to measure distances way out into the cosmos and determine the Hubble constant.
So each rung depends on the calibration of the rung below it.
Precisely. But here's the catch. Like a ladder with a wobbly or incorrectly spaced rung, if there's even a small systematic error or uncertainty in the calibration at any step.
It propagates up the whole ladder and messes up the final result.
Exactly. It can distort the entire distance scale and lead to an incorrect calculation for the Hubble constant. So strengthening each rung, especially the lower, foundational ones, is absolutely crucial.
So what did Skolnick's team do specifically?
Skolnick's team focused on anchoring this cosmic distance ladder more accurately, specifically trying to reduce uncertainties in the local measurements using Type Ia supernovae, but in a slightly different way. They leveraged precise measurements from the Dark Energy Spectroscopic Instrument, or DSI.
DSI? What's that?
DSI is a major ongoing survey mapping the positions and redshifts of tens of millions of galaxies and quasars to create the most detailed 3D map of the universe ever made. It's primarily designed to study dark energy using baryon acoustic oscillations, but its data can help in other ways too. Skolnick realized that a critical step towards solving the issue involved getting a better handle on the distance to the Coma cluster. This is one of the nearest, richest galaxy clusters to Earth, relatively speaking, in our backyard, and about 320 million light years away. It's a crucial anchor point.
Why is Coma so important?
Because it's close enough to study relatively well, but far enough away that the galaxies within it are mostly moving due to the overall cosmic expansion, the Hubble flow, rather than just peculiar local motions. Getting its distance right provides a strong calibration point.
So how do they measure its distance more accurately?
They use new, high-precision data from 12 Type Ia supernovae specifically observed within the Coma cluster itself. As we discussed, these supernovae are vital tools. By meticulously comparing their observed brightness to their known intrinsic luminosity, the team could calculate their precise distance, and thus the distance to the cluster as a whole.
So 12 standard candles all in the same place gave them a really solid distance.
Exactly. Their combined measurement gave a distance to the Coma cluster of roughly 320 million light years away, providing a solid foundation for the rest of their work. This significantly reduced a key source of uncertainty in that part of the distance ladder.
And was this measurement independent of the usual debates?
That's a key point Skolnick emphasized. This specific measurement isn't biased by how we think the Hubble tension story will end. It's an independent, robust calibration point that stands on its own, based purely on supernova physics within that cluster.
Okay, so they nailed down the distance to Coma. Then what?
With that critical rung of the ladder calibrated with unprecedented precision, the team went on to refine the rest of the ladder, connecting the Coma cluster distance to measurements of more distant Type Ia supernovae used in cosmological analyses. their final calculation of the Hubble constant using this improved calibration.
What did they get? Closer to the CMB value?
No, they got a value of around 76.5 kilometers per megaparsec.
76.5. That's even higher than the typical 73-74 value from the SHES team.
It is. It corresponds incredibly closely to the previously measured expansion rates in our local universe from other supernova analyses, and it significantly exceeds predictions from the early universe based on the CMB.
So this doesn't resolve the tension at all. If anything, it reinforces it from the local measurement side.
Exactly. Reinforces the idea that the tension is real, and it's not simply going away with more precise measurements of the local universe. If anything, it slightly widens the gap.
Wow, so this is where the cosmic mystery really deepens. The more precisely we measure this local expansion rate, and the more consistently it deviates from the early universe predictions, the more profound the implications become.
It feels less and less like a simple miscalculation.
And more like a fundamental clash of ideas, or maybe missing physics.
Indeed, this discrepancy is far more than just a minor miscalculation. For decades, cosmological models have relied on the assumption that the universe's expansion rate should be the same, whether measured through the ancient distant universe via the CMB, or locally in the more recent cosmic past, assuming we account for dark energy correctly in the lambda CDM model.
But they're not the same.
The consistent, increasing disagreement between these two independent approaches strongly suggests that something in the standard model of cosmology may be amiss. It points to the alarming possibility that the ACDM model might be fundamentally flawed, or at the very least, incomplete.
That's a huge statement. Lambda CDM has been so successful.
It has been incredibly successful at describing a vast range of observations. That's what makes this tension so compelling and, well, worrying for cosmologists. It's hitting the model where it seems strong as its ability to connect the early universe to the present day.
So this crisis in cosmology is forcing researchers to consider truly radical solutions.
Absolutely. It's pushing the boundaries of physics. It could signal new physics waiting to be discovered.
Like what kind of new physics?
Maybe unknown forces influencing cosmic expansion that only manifested later in the universe's history, after the CMB formed. Perhaps additional particles we haven't detected that interact with dark energy or dark matter in unexpected ways. Maybe even subtle tweaks in the fundamental constants of physics that we thought were immutable over cosmic time.
Or maybe general relativity itself needs modification.
That's definitely on the table. It's possible that entirely new theories of gravity or dark energy are needed to explain this discrepancy. Or, maybe more simply, it could be that we simply haven't accounted for some effects of the universe's expansion that we don't fully understand yet, perhaps related to inhomogeneities or the way structure forms.
It sounds like all bets are off.
Not quite. Lambda CDM still explains a lot. But this ongoing tension forces researchers to question long-held assumptions and find ultimate models. It ensures critical thinking and scientific inquiry remain at the absolute forefront of cosmological research. It's an incredibly exciting, albeit challenging, time to be a cosmologist. The universe might be trying to tell us something fundamental.
It truly is. So what does this all mean for understanding our universe? This Hubble tension is like a cosmic signpost, pointing us towards either hidden complexities in our measurements or entirely new physics. Let's broaden our view now. Are there other pieces of evidence that support accelerated expansion, besides the supernovae? And what other speculative theories are out there trying to resolve this growing cosmic puzzle?
Absolutely. Beyond supernovae, there are several other independent lines of evidence that strongly support the idea of accelerating expansion, which actually makes the Hubble tension even more puzzling because the acceleration itself seems real.
Okay, what are they?
One key piece comes from baryon acoustic oscillations, or BAO.
BAO. Sounds technical.
It is a bit, but the concept is cool. Imagine the early universe, before atoms formed, that hot, dense primordial plasma of photons, protons, and electrons, like a thick, turbulent soup.
Right, the state before the CMB was released.
Exactly. Points of higher density in this photon baryon plasma would start to collapse under gravity. But as they got compressed, the intense pressure from the trapped photons pushed back outwards, creating ripples or vibrations spreading through the plasma. Very much analogous to sound waves rippling through air or water.
Okay, sound waves in the early universe.
Right. Now, dark matter, which was also present but doesn't interact with light, just stayed put at the center of the initial overdensity. When the universe cooled enough for neutral atoms to form recombination, around 380,000 years after the Big Bang, the photons decoupled and streamed away, becoming the CMB.
And the sound waves stopped.
Essentially, yes. The pressure support vanished. This froze the sound waves, leaving behind spherical shells of slightly higher ordinary baryonic matter density at a specific distance from the original dark matter clumps. This distance is set by how far the sound wave could travel before recombination. It's called the sound horizon.
So like a fixed-size ripple frozen in space.
Exactly. A standard ruler imprinted on the distribution of matter. As the universe expanded over billions of years, galaxies tended to form preferentially in these denser regions, both at the center, where the dark matter was, and on these shells.
So galaxies should be slightly more likely to be found separated by that specific distance.
Precisely. By mapping the positions of millions of galaxies today, we can statistically detect this preferred separation scale, a bump in the galaxy correlation function. We see this bump at a distance corresponding to about 150 megaparsecs, or roughly 500 million light years today.
Okay, so we can measure this standard ruler. How does that tell us about acceleration?
Because we know the physical size of this sound horizon ruler very accurately from the CMB data. By measuring how large this ruler appears at different distances, or redshifts, we can map out the expansion history of the universe. Comparing the apparent size of this standard ruler at various cosmic epochs to its known physical size confirms the accelerating expansion. The data fits an accelerating universe much better than a decelerating one.
Wow, that's clever. Independent confirmation from galaxy clustering. What else?
Further evidence comes from studying clusters of galaxies. These are the largest gravitationally bound structures in the universe, formed from the biggest initial density peaks. Their number and distribution are very sensitive to the underlying cosmology, especially the amount of dark matter, which provides the gravitational scaffolding, and dark energy, which resists structure formation through acceleration.
So counting clusters tells us about dark energy.
In a way, yes. By measuring the mass function of galaxy clusters, essentially, how many clusters exist above a certain mass at different redshifts, and comparing these counts to predictions from different cosmological models, we can constrain parameters like W for dark energy and the total matter density. These observations consistently confirm a low matter density and a non-zero amount of dark energy needed to explain the observed cluster counts, again supporting acceleration.
Okay, BAO and clusters. Anything else?
We can also look at the age of the universe. Our best estimates for the age of the universe come from various methods analyzing the oldest stars, like those in globular clusters, and again, fitting cosmological models to the CMB and expansion data. A universe that has always been decelerating would need to be much older than our current estimate of about 13.8 billion years to have reached its current size and expansion rate.
Why older?
Because if it was always slowing down, it must have been expanding much faster in the past to reach its current state. But the ages of the oldest stars put a firm lower limit on the universe's age. Only a model where expansion was slower in the past and is accelerating now fits both the observed expansion rate today and the estimated age of the universe and its oldest objects. The timeline only makes sense with acceleration.
That's a neat consistency check.
And more recently, as we touched on, the advent of gravitational waves as standard sirens has opened up an entirely new window.
Right, merging black holes and neutron stars.
Exactly. The groundbreaking discoveries by LIGO and Virgo not only confirmed Einstein's predictions, but provided a novel way to measure cosmic distances, completely independent of light-based methods like supernovae or Cepheids.
How do gravitational waves measure distance?
The amplitude or strength of the gravitational waves detected depends on the masses of the merging objects and, crucially, their distance from us. If we can estimate the masses from the shape of the wave signal, the chirp, we can infer the distance.
A standard siren, because the loudness tells you the distance, like a siren of known volume.
Precisely. Now, if we could also identify an electromagnetic counterpart, like the kilonova explosion seen after the binary neutron-star merger, GW178087, we can measure the redshift of the host galaxy. Distance plus redshift gives you a measurement of the Hubble constant.
And what did GW17708717 find?
That first standard siren measurement yielded a value for HROs of about 70 kilometers per second per megaparsec.
70, that's kind of right in the middle of the tension.
It is. Intriguingly, it's smack dab between the CMB value, 67.4, and the local ladder value, 73.76. Now, this was just one event, so the uncertainty was still quite large. But as we detect more standard sirens, this method promises to provide a crucial independent cross-check on the Hubble constant and potentially help resolve the tension.
Okay, so the evidence for acceleration itself seems pretty robust from multiple angles: supernovae, BAO, clusters, age, maybe even gravitational waves, which makes the Hubble tension, the disagreement on the rate of that acceleration today, even more significant.
Exactly. It suggests the acceleration is real, but our standard lambda CDM model might not be correctly describing how the universe got from the early state, measured by the CMB, to the current expansion rate measured locally.
So given this robust evidence for acceleration and the stubborn, persistent Hubble tension, what are the proposed solutions? What cosmic tweaks or entirely new rules might be needed to reconcile these conflicting clues?
Well, broadly speaking, the solutions fall into a few categories. Some involve tweaking the existing lambda CDM model, perhaps by introducing new components or changing the behavior of existing ones, particularly around the time of recombination or later.
Okay, like modifying the standard recipe slightly.
Right. One idea we mentioned earlier is phantom energy, or more generally a dark energy, whose equation of state W is not exactly -1. If W evolved over time, perhaps being different in the early universe compared to today, that could potentially bridge the gap. For instance, a phantom fluid with W -1 recently could change the current rate of expansion without disturbing earlier measurements from the CMB significantly.
So dark energy itself might be more complicated than just lambda.
That's one possibility. Another approach focuses on the period before the CMB was formed. This is the idea of early dark energy, EDE.
Adding something extra way back then.
Exactly. Think of our universe's energy budget as a giant cake. Adding a bit more frosting, a temporary burst of additional energy density just before recombination might change things subtly. This early dark energy would need to contribute significantly for a short period and then decay away quickly so it doesn't mess up later cosmology too much.
How would that help the tension?
Such a burst would slightly diminish the physical size of the sound horizon at the time of recombination. Remember that standard ruler from BAO and the CMB? EDE makes the ruler physically smaller than assumed in the standard lambda CDM fit to the CMB.
Okay, smaller ruler.
If the ruler used to calibrate the CMB predictions was actually smaller than to match the observed angular size of the CMB fluctuations, the universe would have to be expanding faster today. This reduction in the inferred physical size of the ruler allows for a higher predicted value of HEO from the CMB, bringing it closer to the local measurements and potentially resolving the tension.
So it tweaks the interpretation of the CMB data itself by changing the early universe physics.
Precisely. EDE models are being actively investigated, though they need careful tuning to avoid conflicting with other cosmological data.
Okay, so modifying dark energy or adding early dark energy are possibilities within a broadly similar framework. What about more radical ideas?
Beyond these, there are even more alternative explanations that challenge fundamental assumptions. Negative mass cosmology, for example, explores the implications if the universe contained negative mass components, which would gravitate repulsively. Perhaps the acceleration isn't due to dark energy, but to the large-scale effects of negative mass.
Negative mass, does that even exist?
Highly speculative, with no experimental evidence, but theoretically explored. Then there's the idea of a dark fluid, attempting to unite dark matter and dark energy into a single substance that behaves differently at different scales, clumping like matter locally, but driving acceleration globally.
One fluid to rule them all.
That's the ambition. Again, very theoretical. There's also the truly exotic idea of repulsive gravitational interaction of antimatter, if antimatter fell up instead of down.
Wouldn't we have noticed that?
Current experiments at CERN are testing this, but strongly suggest antimatter falls normally, like matter, so probably not the answer. More seriously considered are deviations of gravitational laws from general relativity on cosmic scales, like theories of massive gravity, where the graviton particle has a tiny mass.
Changing gravity itself.
Yes. However, many of these modified gravity theories were severely constrained, if not outright ruled out, by that gravitational wave event GW1 Synsic GW817. The fact that gravitational waves arrived almost simultaneously with light from the merger show that gravity propagates at the speed of light to incredible precision, which many modified gravity theories predict shouldn't happen.
So modifying gravity is harder than it sounds.
It's very difficult to do without breaking other things that work well.
Okay, what else is out there in the realm of maybe less likely ideas?
A fascinating, if perhaps unlikely alternative is the back reaction conjecture associated with cosmologist Sixi Razanen. The core idea is that maybe the expansion rate isn't perfectly uniform everywhere. Perhaps we live in a region where expansion is just locally faster than the true cosmic average.
Like we're in a cosmic fast lane.
Sort of. The mechanism suggests that inhomogeneities in the early universe led to the formation of vast walls and bubbles of varying density. If our observable universe happens to reside within a large, underdense region, a bubble with less matter than average,
then gravity would be weaker here.
Exactly. Space within our bubble would be less curved, making it appear to have more volume and thus a higher local expansion rate compared to denser regions, which would expand slower. The implication is that the averaging process used in standard models might be too simplistic, and what we perceive as acceleration could be an illusion arising from these large-scale structures, the back reaction of structure formation on the overall expansion metric.
So no dark energy needed, just lumpiness.
That's the idea. However, Rosanen himself notes it's probably unlikely to explain the whole effect, as it would require rather large density fluctuations, 20%, on very large scales, much larger than typically observed or expected.
Okay, interesting, but maybe a long shot. Any other really out there ideas?
Well, there's shockwave cosmology, proposed by Joel Smoller and Blake Temple back in 2003. Their core idea is truly wild. Maybe the Big Bang wasn't the beginning of everything, but was actually an explosion inside a pre-existing black hole, creating our observable universe as a kind of expanding wavefront within it.
Whoa, the universe is inside a black hole.
That's the premise. An extension of this theory suggests that the shockwave from this internal explosion might have resulted in our specific part of the universe having a lower density than surrounding regions, which could mimic the effects of cosmic acceleration without needing dark energy.
Can that be tested?
It actually makes a specific testable prediction. It predicts a different value for the third derivative of the expansion history, the jerk, or cubic correction to redshift versus luminosity, predicting a value c equals 0.359 compared to standard dark energy models, which predicts c around nigh to 0.180. However, for this model to be taken seriously, it still needs to successfully explain all the other key cosmological observations like the CMB, nucleosynthesis, galaxy surveys, etc., which is a major hurdle.
So, intriguing prediction, but lots of work needed. What about simpler explanations? Could it just be we're measuring things wrong or our location is weird?
That's the final category. The possibility that dark energy, and perhaps the Hubble tension, is an illusion caused by some measurement bias or our specific location. We touched on the back reaction idea, but maybe even simpler effects are at play. If we are located in an emptier than average region of space, a cosmic void.
The Hubble bubble idea.
Right. The cumulative effect of being in a large void could make the local expansion rate appear higher than the true global average, potentially creating the illusion of cosmic acceleration, or at least contributing to the Hubble tension. Studies suggest that this effect is likely too small to explain the whole discrepancy, but it might play a role.
Or maybe issues with the supernovae themselves.
People constantly reevaluate the standard candle assumption.
Right.
Are type Ia supernovae really perfectly standard? Do their properties evolve subtly with cosmic time or environment in ways we haven't fully accounted for? Could there be selection biases in the samples? These are actively researched, but so far no clear systematic error has been found that resolves the tension. It seems robust.
So we're left with this profound puzzle. Acceleration seems real, supported by multiple lines of evidence, but the rate is disputed, potentially pointing to flaws in our standard model or even completely new physics.
That's the state of play. A fascinating, confusing, and exciting time in cosmology.
So with all these possibilities swirling around and the relentless march of dark energy seemingly dominating the universe, what does an ever-expanding, perhaps accelerating universe truly mean for the ultimate fate of galaxies, stars, and indeed life itself? Where's this all heading?
That's the ultimate question, isn't it? What's fascinating here is that as the universe continues to expand, the density of radiation and ordinary matter, both baryonic and dark matter, keeps declining as they spread out over larger volumes. But the density of dark energy...
If it's the cosmological constant, stays constant.
Exactly. Or at least decreases much more slowly than matter. So inevitably, dark energy becomes completely dominant, controlling the universe's fate. If dark energy is indeed the cosmological constant, WOBO5=1, as in the standard ACDM model, its constant energy density means its repulsive force becomes increasingly overwhelming as space stretches,
pushing everything apart faster and faster.
Yes. In such models, the universe will expand exponentially with time in the far, far future. It evolves into what's known as a de Sitter universe, essentially, an empty universe dominated by vacuum energy, expanding relentlessly.
Empty? What happens to all the stuff?
Well, the first profound consequence is that all evidence for the Big Bang will eventually disappear from view. As the universe expands exponentially, distant galaxies will accelerate away from us so fast that their light will never reach us. They'll recede beyond our cosmic horizon.
We'll be isolated.
Effectively, yes. Our local group of galaxies might remain bound together for a while, but everything else will vanish from sight. Even the cosmic microwave background, that crucial echo of the universe's birth, will continue to redshift to incredibly lower intensities and much longer wavelengths, becoming practically imperceptible.
So future astronomers won't even know there was a Big Bang.
Eventually, yes. Its frequency will become so low that it will be absorbed by the interstellar medium within our local remnants, effectively screening it from any observer. This could occur when the universe is perhaps less than 50 times its existing age. It could lead to the end of cosmology as an observational science, and eventually the end of any life, as the distant universe turns dark and all the historical markers of its origin fade away. Future civilizations, if any exist, might conclude they live in a static, empty island universe.
That's a chilling thought. What happens after that? Just endless expansion.
It leads to what scientists commonly call the heat death of the universe, or sometimes the big freeze. In this constantly expanding universe dominated by a cosmological constant, everything just winds down. Stars will eventually burn out. Black holes will evaporate over immense timescales due to Hawking radiation. Even protons themselves might decay if theories predicting proton decay are correct.
So everything disintegrates.
Eventually, yes. All matter will ionize and disintegrate into isolated stable particles such as electrons and neutrinos and maybe photons, all complex structures dissipating. The universe will approach a state of maximum entropy, an infinitely cold, dark, and empty void, with virtually no energy gradients left to power any processes or form any structure. A truly quiescent and featureless cosmic landscape. Forever.
Unless it's phantom energy and the big rip happens first.
Unless that happens first, yes. That would be a much more violent, but perhaps quicker end.
What an incredibly humbling yet awe-inspiring journey we've taken today. We've gone from the universe's lightning-fast birth with inflation.
That incredible initial whoosh.
Through its unexpected and accelerating expansion, driven by the mysterious dark energy.
The great cosmic mystery number 1.
And delved into the thrilling, confusing Hubble tension that's currently challenging our foundational cosmic models.
Cosmic mystery number 2. Maybe linked to number 1.
It's like the universe is constantly keeping us on our toes, a true cosmic detective story unfolding before our very eyes.
Never a dull moment in cosmology.
This is truly an exciting time to be studying cosmology. Every new measurement, every refinement, every persistent discrepancy. It's not a failure, but a remarkable opportunity, isn't it?
Absolutely. These tensions are where discoveries happen. It means there are still profound surprises left in the universe. And who knows what the next breakthrough might be. We could be on the cusp of potentially rewriting fundamental physics.
We are truly living in an era where the universe is like a cosmic jigsaw puzzle, with many pieces still being put together, and maybe some pieces from a different box entirely, forcing us to reevaluate the picture on the lid.
That's a great way to put it. The resolution of the Hubble tension, whatever turns out to be new physics, some subtle systematic we missed, will not only solve a long-standing puzzle, but might open entirely new areas of exploration, broadening our understanding of the universe in ways we can't yet predict. It will fundamentally change our cosmic map.
It just reminds us that we are the brief flare of awareness in a universe that never stops stretching into the unknown, constantly revealing new layers of complexity and wonder.
It's a privilege to be able to even ask these questions. So keep questioning, keep exploring, and keep looking up. The universe has many more secrets yet to reveal, and the journey of discovery is truly far from over.